Hey class, today we've got a long lesson, but it's a really important one. We're looking on pages S8, 9, and 10, starting on page 156 of your manual, from Unit S, Simple Linear Regression. All right, what we're going to be looking at here then is how much of the variation in y is explained by x, and then can we use that to do some hypothesis testing? Let me explain what I mean by that. I'm going to go back up here to the last problem that we dealt with. And if you didn't see these calculations, take a look at the mini lesson that we did on pages S5 to S7. So we looked at the price of the house in thousands of dollars and the size of the house in hundreds of square feet. And we came up with a regression equation that looked like this. So it was this guy right here. So the price is equal to 71.025 times 4.641 times x, which is the size. Or in other words, for every 100 square feet that the size of the house increases, then the price of the house is expected to go up by about $4,600. Now the question that we have is that significant? And when we talk about significance here, we're really asking the question is that slope significantly different from zero? Now you might look at that and say, well, obviously that's different from zero. But what if I did the following here? I'm going to go back up here to the original data. So this is looking at the y variable, and this is in thousands of dollars. What if for some goofy reason I'd actually recorded these values in millions of dollars, so that these actually would be then 0.145. 0.145 million, of course, is 145,000, 0.228 million, and so on like that. Now I could still run a regression on that, but what would happen is that this slope here would end up being 0.00461, or about 0.05. And I look at that and say, well, does that seem to be significantly different from zero? And just by eyeballing it, I'd say, well, no. And another way to think of it this way is that if I change this particular scale here for the price on our graph to millions of dollars instead of increments of 25,000, then I'd end up with a regression line which looks like it's almost completely horizontal. Now, why is that important? Well, think back to Unit C when we talked about the measures of the correlation coefficient R. So R goes from -1 to +1. And when it's 0, it means that x has no effect on y. The two variables are not linearly related to each other. An R of 0 means that it has a slope of 0. If you take a look, just as an aside here, going back to our very last unit where we were calculating the B1 and the B0 values in a regression, you'll remember that the numerator for calculating B1 was the same numerator for calculating R in Unit C. And what that's saying, of course, is that a positive slope, a positive correlation, a negative slope, a negative correlation. A slope of 0, a horizontal line, means we can increase or decrease the x as much as we want, and it has no effect on the y. And so that's an R of 0, a slope of 0. So when we're asking whether a variable is significant at explaining a y variable, some x is significant at explaining a y, one way that we can measure that is the slope equal to 0 or not? Now, if I changed these all to millions, so 0.145, then I'd end up with something that looks like this, and that doesn't look like it's significantly different from 0 just by the magnitude of the numbers. But when we run some tests, which we'll be taking a look at in the next couple of units here, the next couple of mini lessons. And if you take a look at my lab lectures, you'll see that I talk about how to do regression using Excel and how to read the output. And what we found out there actually was that the slope is significant. The p-value is less than 5%, and so it is significant. Now, we'll get to that here, but that's not going to be in this particular lecture. So that's the important thing, is that you can't just look at the magnitude of the numbers and figure out whether they are significant or not. So we're going to go through some steps here and to figure out, well, how do you do a hypothesis test? And so on page S8, we have something called the Components of Variability. And I want you to think of this as being the same as ANOVA, because it actually is. Remember in ANOVA, we had an interval variable. And then what we did was we unstacked it into various columns of the treatments. And then we looked at all of those numbers together and we said, well, what causes the variation of the numbers here? And we called that numerator of the total variance SST. Now, we called it X. Doesn't matter. We'll call this one Y because that's what we're measuring, is the Y variable. But it's the same SST value. It's just the numerator of the total variance of all the Y values. And the question is then, what's causing that variation? Why do house prices go from $150,000 up to $1 million or something like that, right? In ANOVA, what we did was we broke that total SST into two components. The amount of variation between treatments, SSB, and the amount of variation within treatments. And then we took a ratio of the two, SSB over SSW, with some degrees of freedom in there, and we ended up with an F star value, so it was an Anova test. We're going to do the same thing here. There's an Anova test. Thought you were done with Anova, didn't you? There's an Anova test here, and let's take a look at that. Okay, so what I've done here then is I've drawn a little diagram right here. And I want to just label a couple of things here. So this is X is our size of our house, and then our Y is going to be the price of our house up here. And then there's a couple of green lines here that I put in here. And this is the mean of the Y's. So this is the Y bar, and this is the X bar. And remember what we said at the bottom of page, where was it? I think it was S5. We said that the regression line, the sample regression line, which is this guy right here, passes through the point X bar, Y bar. Now, I'm going to put in a point. I'll put it down here. And let's say this is for a 1,500 square foot house. This is a house that is actually selling for less than the average 1,500 square foot house. We would expect that the average 1,500 square foot house would sell for this amount. Let's just call it YI. We'll call this XI right there. So I stands for 1,500 square feet in this case. But we want to take a look at this X value right here. And we want to take a look at three different distances. This distance here is the error term. And it's actually the difference between the actual Y value and the Y hat value, right? So this is the YI value. And then this is the Y hat I. Sorry, I should have put a hat on that over there. So that's that distance there, and it's the error term. Now we've got this distance here, and I'll actually write it on this side here. This is the distance between the Y hat I and the mean of the Y's, that green line. And then finally, we've got this whole area here, and that's from the point up to the green line, and that's going to be the yi minus the y bar. Okay, the yi minus the y bar, that's the point itself up to the green line, is this right here. Why is that important? Well, because when we're calculating the SST value, looking at the total variation of the y values, that's made up of the sum of all of those values, y up any particular yi minus the y bar, squared. And you sum them all up and you get the numerator of the variance. That's the way we've always done it. Same with the x's. But it's broken up into two components. So it's broken up those two areas that I've outlined here. Now, of course, this point here could be above the line. It could be way up here. It could be between the green bar and the red bar, the green bar and the red line. But it doesn't really matter. The distances will just be positive, negative, that kind of stuff. But this relationship here shows us how we can take a particular deviation of a y from its mean and breaking it up into two components. What we do with that is, if you take a look at the formula for variance, is we sum over all the squared deviations to get the SST. And so if we were to sum over all of the squared deviations, then we'd end up with the SST value. Remember I said that this here is the error term? And so if you sum over all of these squared error terms, you get the SSE, which stands for sum of squares error. Let me change that to a different color right there. And then this part here, the SSR, is the variation in y, which is explained by the x variable, by the regression line. Let me show you with another little picture up here. I'm just going to get rid of some of these dots here that came from my palm. Okay. Now, I've drawn something up here that you can see. And I'm going to have here, this will be my x, this will be my y, and so on. And we're going to have a regression line. So let me put that in red, like that. And of course, on a regression line, you've got a bunch of actual observations that are used to come up with that regression line. And if you look at this, you'll see that the y values, of course, have some variation here. The SST. Now, what's the cause of that variation? Well, a big cause of that variation is the regression line itself. That is, as x increases, so does y. Let me give you a goofy way of thinking of this. If I was to put my eyeball down here, let's draw an eyeball. Put in some eyelashes. There we go. So if I looked along that line, that kind of flattens it out so that you don't see the rise. What you would see then is a variation around the regression line, which is your SSE. Okay? So the total variation then in y it goes from here up to here, is caused by the regression line itself, that as x increases, so does y, and then whatever is left over, oops, keeps disappearing there, is the SST, the variation around the regression line. So we've got our two components then. Just like in Anova, we had the total variation in our interval scale variable. Our SST is divided into two components, the amount of variation between treatments, once you divide them into treatments, and variation within. And here it's the same idea. The total variation in y is explained by the x's, which is SSR, and then whatever is left over that we haven't measured, that's the error. Now we'll use that then in calculations for doing hypothesis testing in a couple of pages. But we're going to do some calculations on page S10 in a bit. But before we do that, let's take a look at S9. So there's some formulas here for the Ss values, just like we had in Anova. They're a little different, of course. And then we've got something called the R-squared value, which is, another name for it is the coefficient of determination, or the explained variation, right here. And it's an important term whenever you're looking at an R-squared, taking a look at a regression, because it's talking about the strength of the relationship. R-squared is an aggregate measure. And what I mean by that is that when we get into multiple linear regression in particular, it's looking at the effect of all of the x's together and their effect on y. So when we look at, in Unit M, we'll look at, well, what determines the price of a house? So that will be the y variable. And the x's are going to be things like, well, you've got the size of the house and the age of the house and the number of rooms and bathrooms and garage stalls and things like that. And each of those is a column in a spreadsheet, right? So you might have 100 or 200 observations, but we're talking about the number of x variables. When you take a look at all of those x variables together as an aggregate measure, then we can come up with their correlation with the y variable. And that's called the R-squared value. The square root of that is something called the multiple regression coefficient, the multiple correlation. And don't worry about that. You'll see that in the output. We're interested in the y squared and the R squared. And the R squared is determined by this formula, SSR over SST. It takes on values of 0 to 1 and is generally expressed as a percentage. So we'll take a look at that in a moment. The other thing to keep in mind about R squared here, here's an important relationship, and that is that in a simple linear regression model where you only have one x variable, not x values, I'm talking about x variables, like in our particular case then size, or in another case the age of a person and how it determines the number of push-ups that they can do. Then when you've got one x variable, then its relationship between the x and the y is the little r. And that's just the Pearson's correlation coefficient from Unit C. And if you square that, you'll get the R squared value. So that's a good relationship to know for a simple linear regression model, one x variable, one y variable. But the R square is powerful in that when you get into multiple regression, it's taking a look at the aggregate measure of all of the x's and their effect on y together. All right, one other thing here then is there's something here called the standard error of the estimate, and that's just really the standard deviation of all the error terms, or the residuals. And it's found by the square root of SSE over square root of n minus p minus 1. Now this p is a symbol you haven't seen before. We've seen lots of p's in stats, but this is another one. And it's the number of explanatory variables, number of x variables. So in our particular case, where we have in simple linear regression just one x variable, then that p is equal to 1. In multiple linear regression, it'll be the number of x columns, if you like. Again, not the number of observations, that's the n, but it's the number of x variables. So you lose 1 degree of freedom for every variable, x variable, and then 1 degree of freedom for the y. All right, let's do some calculations. So on page S10, we're going to be using the push-ups and age example. And we originally did this on page S6. So on page S6, you're going to find those summary measures. So you can flip back there and take a look at it. And I'm just going to write down the summary measures that we came up with. So the sum of the x's turned out to be 503 in that problem. Sum of the y's is 261. Sum of the x squares was 25,921. Sum of the y squares was 6531. And the sum of the xy's was equal to 9658. 9658, yeah. And then the n is equal to 12 pairs of numbers. Okay, let's calculate the SST value. And the formula that we use for that then is up here. So we're going to be using these formulas right here for the SS values. Okay? All right, let's take a look at what we've got. SST is equal to the sum of the y squares values minus the square of the sum of y's over n. So in our case then, that's going to be 6531 minus 261 squared over 12. And that comes to 854.25. Okay. SSR is equal to B1 times the sum of the xy's minus the sum of the sum of the y's. You'll recognize that. That was the numerator when you calculated B1 and the numerator when you calculated R. Now, we've calculated B1 before from page S6, and it turned out to be minus 0.265. So that was from page S6. Times 9658 minus 503 times 261 over 12. And that comes to 339.92. And then SSE will be the difference between SST and SSR. So it's going to be 854.25 minus 339.92, and that gives us 514.33. So here's your SSE, here's your SSR, and they add up to your SST, like so. All right, let's calculate the R squared value. R squared is equal to SSR over SST. So that is 339.92 over 854.25, and that comes to 0.398. The interpretation of that is generally we write that as 39.8%. And the interpretation of that is this. We would say 39.8% of the variation can't get that word in there. It's too close to the edge. To the variation in the number of push-ups that a person can do is explained by their age. Okay. Actually, of course, it's taking a look at everybody together, so the 38.9% of the variation in the number of push-ups that people can do, might be better to say, rather than a person. So let me change that to people, is explained by their age. Okay. All right. The other thing, just before we go on here, is remember that we said that for a simple linear regression where you only have one x variable and one y variable, that this relationship holds, that r squared is equal to the little r squared, and that was from unit C, C6, I think it was, and we talked about it in S6. I think that was C7, actually. Let me just flip back here and check. Yeah, that was C7. Okay, let me just change that. There we go. And S6. All right, so that's going to be r squared 0.398 is equal to minus 0.631 squared. And we know that this is negative here because the slope was negative. All right, one more thing to do in this problem here, and that's calculate the SE value. Let me do it up here. So up here, let's do that. So the SE is equal to the square root of SSE over n minus p minus 1. So that's equal to the square root of 514.33 over 12 minus 1 minus 1. Remember, the middle 1 stands for the number of x variables. So there's just one x variable here, which is age. So it would be the square root of 51.43, and that comes to 7.17. So that's the standard deviation of all the error terms or the residuals. All right. Let's take a look at this other problem. I know this is a long lesson, but let's push through and actually do this. Of course, the hope is that you'll stop the video at this point and you'll go and try this for the house and weight examples, but I'm going to assume that you've done that and just push through with this. So the values that we've got here from page S7 were the sum of the x's were 165. Sum of the y's is 1334. Sum of the x squared values is 3855. Sum of the y square values is 241, 394. The sum of the xy's are 29,611, and the n was 8. 8 houses, each with a size and a price. Okay, SST. SST is equal to sum of the y squares minus square the sum of y's over n. So the y squares, 241, 394 minus 1334 squared over 8 is equal to, it's a big number, it's 18,949.50. SSR is equal to B1 times sum of the xy's minus sum of x, sum of y over n. And that's equal to 4.641, and that's from page S7, times 29,611 minus 165 times 1334 over 8. And that comes to 9733.79. And then SSE will be SST minus SSR. So it's going to be 18,949.50 minus 9733.79. And that's going to end up being 9215.71. So here's your SSE, your SSR, and they add up to SST. Okay. Hey, one thing that's really important here as you go through this is to make sure that none of these SS values turn out to be negative. Remember, they're a sum of squares. And so you can't have negative values. If that happens, maybe just scratch down a note or something. If you were to do this longhand or something, and say that these shouldn't be negative. Okay, so you must have made a calculation error somewhere. R squared will be equal to SSR over SST. And so that will be 9733.79 over 18,949.50. And that's going to turn out to be 0.514, or 51.4% of the variation in the selling price of a house, of the price of the house, is explained by the size. Okay, one other calculation. We'll do it over here. The the SE value. The SE value is equal to the square root of the SSE over n minus p minus 1. So that would be the square root of 9215.71 divided by 8 minus 1 minus 1. Take the square root of that and you'll get 39.19, and that is the square root. That's the standard deviation of the error terms, the residuals. So we're going to use that stuff later in the next lesson to take a look at the hypothesis tests for the slope and the intercept and confidence intervals and all sorts of exciting stuff. And I'm going to end the lesson right here. Thanks for listening.